Good morning, ladies and gentlemen. Good evening and good afternoon. This is the plenary talk from Professor Nao Hirokawa from JAIST, and is the plenary talk from the area of theory of computation. Nao Hirokawa is a doctor from the University of Innsbruck in Austria. He was supervised by an important figure in term rewriting systems, Professor R. Middeldorf, and now is one of the most important researchers in the area of rewriting. That is the basic area of the group of theory of computation at the University of Brasilia, say the central area for use. And now is famous because his work on applying rewriting techniques to automate termination. He was involved in the development of a famous tool to check termination of programs and functions that is called the Tyrolean termination tool, and is involved in the steering committees of two important workshops in confluence and termination that are also the central properties of term rewriting systems. Please now. Thank you very much for coming, of course, and for accepting our invitation and for your willingness to give a talk for this summer workshop in mathematics in Brazil.
Okay, yeah, thank you very much for kind introduction. My name is Nao Hirokawa, and as he mentioned, my main research topic is interested in automatic analysis of various properties like termination, confluence, and also complexity analysis. Okay, so let me start from a small quiz. Okay, so actually this is a term-like system. You see, and if this is equality, then these two actions are just a usual action for addition of pair arithmetic. But here we are interested in how to compute these numbers, like addition of 1 plus 2. So instead of equality, I use arrow notation here. And calculation rule is just like normal equation-based reasoning. So for instance, here, this is 1 plus 2. 1 plus 2 is computed by pattern matching. So you see, second equation, second rule can be applied to the current term. Just a moment, perhaps I have some echo problem. So just a moment. Okay, I think now it's okay. Okay, you see, this left-hand side of the second rule matches with the current term. Okay, and if we substitute suitable terms, these terms, into x and y, we obtain this term. Okay, and this term, okay, this term can be still rewritten by using the second rule. So now we obtain this term. And the second rule cannot be applied anymore. However, a first rule can apply to this subterm. Okay, now we obtain successor of 0. So this means that 3. Okay, 1 plus 2 makes 3. So this is correct computation. Now, this is the main topic in this talk. How many steps do we need to perform in order to compute addition of k plus m? So this is the question. You see, I mean, if k is 1 and m is 2, we need 3 steps, right, to obtain the final result. Perhaps, I mean, you can easily imagine the number of steps for this case. I mean, you see, I mean, this is 2, and here we have, I mean, 2 steps. And the final one, there is 0, right? So this takes 6 steps, right? Basically, 5 plus 1. And we can generalize this setting. So namely, in order to compute this term, we actually need m plus 1 steps. Okay, so this is actually the complexity of function computation. Okay, especially in this case, it's addition. Okay, so addition in this system, addition can be computed in linear time. Okay, now let's make a problem setting more complex. So here I put new rules for multiplication. Calculation is just like this. By the way, how to read? I mean, x times 0 is 0. I mean, this is easy, right? X times 0 is 0. What it is? I mean, this is, I mean, x times y plus 1. This is just a distribution, right? So x times y plus x, right? So this is the usual definition of multiplication. And the computation is like this. So 1 times 1. Okay, so by using the fourth rule, we obtain this little bit complex term. But it's not difficult. 1 plus 1 times 1 is 1 times 0 plus 1. Okay, and of course 1 times 0 is 0. So remaining part is just addition. So we obtain 1 in the end, right? But actually, there is another path to obtain 1. So you see here, instead of computing multiplication, we can compute addition because second rule can apply. And then we obtain a successor of something, right? And again, we can compute addition. Okay, now inside the term is multiplication of 1 and 0. And yeah, performing the third rule, we obtain 1. Okay, so of course, there are many ways to compute given expressions. But for this setting, we have the same result. Okay, so piano actions is consistent, basically, at least for addition and multiplication. Okay, now I want to ask you about the complexity of multiplication function. So suppose first argument is k and second argument is m. How many steps do we need in worst case? Worst case means the longest case. of these sequences. Yeah, this is a bit difficult question, but I think, you can easily imagine that this would be something, the number which can be bound by this big O notation. Right. So later, I want to explain how to analyze this kind of asymptotic complexity with respect to the size of input term. Right. So this is the introduction to this talk. So main aim of this talk is to discuss how to analyze runtime complexity, time complexity of functions. So just like this. So suppose program is written in term rewriting format, and inputting such a program to some tool, automatic tool, and then tool analyzes time complexity of given program, and then it output time complexity. Okay, this is actually time complexity. For instance, if we put a merge sort, and then expected answer is n log n. And yeah, why do we need to analyze complexities, time complexities? Yeah, perhaps, this is an important question. Of course, one reason is in order to detect performance bugs. Do you know, for instance, balanced search tree algorithms? There is famous algorithm based on variations of ABL trees. There was some bug in implementations, many implementations, including Haskell and OCaml libraries. And yeah, actually, n log n time algorithm was expected, but corresponding implementation took quadratic time. So this kind of performance bug causes a problem in our real life. So sometimes we want to seriously detect some weak point of efficiency of a program. Yeah, another reason to analyze complexity is detecting bugs or vulnerable code. So for instance, if program contains a bug, usually quite often complexity of the program changes. So for instance, if our program contains some bug that allows us to execute arbitrary code, and then no longer expected, some polynomial time upper bound can be guaranteed. So if we have a complexity analyzer, we can identify some function that has some vulnerable code, for instance. But more honestly, I'm working on complexity analysis just to satisfy my curiosity. So given a code, I want to know exact complexity. Right, so this is background, and the remaining part of this talk are actually consisting of 4 parts. First, I want to formally define the notion of runtime complexity that will be discussed in this talk. And the second part discusses how to analyze runtime complexity. And the third part is some little bit more advanced topic. And here we will discuss how to analyze innermost runtime complexity. This means that runtime complexity with respect to eager evaluation or innermost rewriting. And the fourth part is about just a demonstration of presented techniques. And here I will show some how insertion sort algorithm, complexity of insertion sort algorithm and merge sort algorithm can be analyzed by presented technique. Right. By the way, third one is new result, and this is obtained by joint work with my student, Tsuchiya Tomoyuki. Right, so let me start from defining the notion of runtime complexity. We need to distinguish symbols. The root symbol of the left-hand side of each rule is called defined symbols. And the remaining symbols are called constructor symbols. And here, this is our target term. It is called a basic term. Basic term consists of single defined symbol that occurs at the root position and constructor argument terms. Okay, so only root symbol is defined symbol and the remaining part are non-defined symbols or variables. And the runtime complexity is just a maximum length of basic term of size given n. Okay. And yeah, what kind of terms are basic term? Yeah, for instance, this is basic term. You see, addition is our defined symbol, and successor symbols are not defined symbols. Okay, so this is basic term. But yeah, this one is not basic because here we have defined symbol. This is okay, but the problem is this one. You see, argument of multiplication contains another defined symbol because we want to analyze complexities of functions. So we don't want to include another function symbol in the initial term. Right, so this is the notion of basic term and runtime complexity. Okay, so for instance, this one, okay, this one is a previous system. And now we can talk about the runtime complexity of this system. Actually, the runtime complexity of this system is linear. Okay, why? Because every basic term is this kind of form. Okay, so addition is, okay, we have addition and whose argument are constructor terms like successor of 0, 0, or something like that. Okay, this kind of terms are argument position. Okay, and for such a basic term, always the term terminates within n steps. Here, n stands for the size of this term. Okay, and then we can bound the runtime complexity function from above by this number. You see, basically, computation of addition takes only m steps plus 1, right? So this number suffices to give a upper bound of this function. Okay, and if we replace this number by n, this is linear function. So we obtain linear upper bound. Okay, so this is basically informal reasoning for the runtime complexity. Now, we want to formally analyze runtime complexity instead of this kind of informal discussion argument. Okay, and let me remark 2 things. Yeah, first of all, this is runtime complexity is basically time complexity for function computation. Okay, that's why we only deal with basic term. Okay, so and if we consider arbitrary term structure, then actually there is a term that takes quadratic, okay, number of steps. Okay, for instance, this is such an instance. In order to compute this term, we need a quadratic number of rewrite steps to get the normal form or computational result. Right. Okay. And now let me recall the system for multiplication. Okay, actually this is, small quiz. Is the runtime complexity constant? Actually, I'm not sure. Can I see the comment? Maybe only good morning comment. Okay, so I will answer by myself. Yeah, actually, this is not constant because in order to compute this term, we need steps linear. Actually, proportional to n. Okay. Is this linear time? Actually, no. In order to compute multiplication of 1 times n, okay, this goes to addition of 1 and addition of 1. So basically, we need to compute this term. So runtime complexity of this system is at least quadratic time. Is this quadratic? Actually, yes. But the question is how to prove it. Soon later, I will explain how this complexity can be proved. But in order to prove it, we need to introduce algebras to estimate a complexity bound. Okay, so let me first define the notion of algebras. Algebras, actually universal algebra, consists of carrier and interpretations. Interpretations maps function symbol to real mathematical functions. And in order to interpret variables, we need assignment. This is just a function from variables to the given carrier. And terms are interpreted as follows. Variable is interpreted by assignment, and this kind of term is interpreted by just replacing function symbol by given interpreted version of function. For instance, if we define interpretations like this, so 0 is 0, successor is successor, addition is not addition, but some strange term. So here we multiply second argument by 2 and plus 1. This is very strange interpretations, but this is useful for analyzing complexities. For instance, this term is basically 1 plus 2, but this is interpreted as follows. First, function symbols, all function symbols are replaced by interpreted version of functions. Okay, so now 0 is 0, successor is plus 1 function, so this is 1, this is 0, this is 1, and this is 2. According to the definition of addition, we multiply 2 by 2 and plus 1, so this is 4. No, 1 plus 4 plus 1, so 6. You see? 6. Okay? So by using this kind of valuation, interpretation of terms, this previous rewrite sequence can be evaluated to these sequence. Okay? So actually, first term is 6, second term is 5, third one is 4, and last one is 3. Okay? Important point is every rewrite step decreases the corresponding values. Okay? So this 6 means this term cannot rewrite more than 6 times because our interpretations is given on the domain natural numbers. So we cannot go down below 0. Okay? What this means? So if we compute this value, we know the termination measure of given term, t. Okay, and for this setting, this value is bound by 2 times n. Here, n stands for the size of t. Okay, so this means that we may conclude linear runtime complexity for this system. Okay, so let me formalize the corresponding theorem. So suppose A is algebra based on natural numbers, and S and T are term. And here I use this notation if inequality holds for interpreted values of terms. And algebra is called constructor-restricted if all constructor symbols are the interpreted value of all constructor symbols are bounded by this formula. Okay, so basically constructor symbols, you see, this part is constructor symbol. Okay, and this is just a summation of argument. Okay, plus some constant number. Okay, this is basically summation of argument plus some constant number. Then interpretations are called constructor restricted, and such a algebra is also called constructor restricted. Okay, and Bonfim, Kishon, Marion, and Tuzet proved the following theorem. Runtime complexity is actually bound by d-degree polynomial function if we can find a suitable algebra that is constructor restricted, strictly monotone, and this inclusion holds. So namely, all rewrite rules are oriented by the induced ordering. Okay? And what is this D? D is just a maximum degree of polynomials, okay, that defines interpretations. Okay, the proof is very easy because under this setting, interpretation can be bound by such a formula. Right, so let's use this theorem to determine runtime complexity. Okay, so procedure is as follows. So for given TRS, we try to find a constructor-restricted, strictly monotone, linear polynomial interpretation because we want to show linear runtime complexity for this system. Okay, and this is a suitable interpretation, and all rules are oriented by these interpretations. So, according to the previous theorem, we may conclude linear runtime complexity. Good. Okay, what about the case of multiplication? And actually, quadratic means this one. Quadratic polynomial interpretation exists. You see, quadratic formula. And by using this interpretation, we may orient all rewrite rules like this. Okay? And you see, this is, degree 2, actually, summation of all each degree of indeterminate is 2, right? Maximum 2. So we can conclude the runtime complexity is quadratic. So namely, runtime complexity function is bound by some function that belongs to this class. Good. Okay, but you see, in order to analyze complexities, we need to find a suitable interpretation. Okay, and even if we find a suitable interpretation, still we need to verify inequalities of polynomials. And probably you know Diophantine problem is undecidable. Okay, undecidability of Diophantine constraint is known. So even if we fix an algebra, still this inclusion is undecidable. But nowadays, there is a good approximation method. So by using such an approximation method, we can automatically verify such inequalities. Okay, but still finding suitable interpretation is quite difficult problem. But rewriting community worked on this topic for a long time. And today, interpretations are found by SMT solvers. So idea is very simple. Okay, instead of concrete polynomial, we use parameterized version of polynomials. So namely, unknown coefficients are used to specify interpretations. Okay, and we just compute both sides. Okay, and then we obtain such horrible constraint. Okay, this is parameter, you see, and this is x and y are universally quantified. Okay, and monotonicity condition is just can be approximated by these conditions. Okay, and performing quantifier elimination, we may obtain we obtain such a quantifier-free arithmetic formula. Okay, and quantifier-free non-linear arithmetic, non-linear integer arithmetic SMT solvers, we can find suitable solutions like this. Okay, so basically this is a basic structure to automatically analyze runtime complexity. Okay, this is a very basic method and actually easy to automate if you adapt SMT solvers. Right. But power is perhaps a little bit weak. Actually, not a little bit. Power is quite weak if you want to analyze more practical algorithms or some programs. Okay, so let me remark some issue on complexity bug or performance bug. This is previous our rewrite system for multiplication. You see, this is quadratic time, runtime complexity. Okay, quadratic time. But if we swap, okay, these arguments. I'm sorry. If we, no, sorry. The previous one was this one. Okay. Let me erase. Okay. Sorry. Okay. Actually, this was typo. I'm sorry. This was quadratic runtime complexity. But if we exchange them, so namely this one, then the runtime complexity becomes cubic time, and it is no longer quadratic time. This is a bit shocking result for me, actually. You see, complexity is really difficult to analyze for human. So sometimes we implement algorithm with minor modification, but this may cause some performance bug in the end. Right. Good. Yeah, this is just some history about interpretation method. So the method that just I explained is due to Bonfante et al. And after that, people investigated matrix interpretations. Matrix, so namely, rather than single natural numbers, they used, for instance, a pair of numbers based on matrix computation. And this method was further refined to the notion of spectral radius theory. And even this method was related to weighted automata-based complexity analysis. And very recently, Kopp and Weil introduced tuple interpretations in order to give some tight upper bound of runtime complexities. Okay, but this is about history. Right, so let me introduce another topic, so namely innermost complexity analysis. So far, our rewrite step is arbitrary rewrite step, but from now on, we concentrate on innermost rewrite step. Okay, so innermost rewrite step means that the arguments are always computed before outermost position. Okay, so before calling a function, we compute argument. Okay, and if we restrict our strategy to our evaluation strategy to innermost one, and then we may benefit from such a restricted computation. And in order to exploit it, first let's observe the role of algebras. Okay, so this is in previous algebra that were used for complexity of addition. And this algebra, for instance, evaluates this term to 2 based on these interpretations. But actually, there are 2 roles, you see. Actually, we used this value for termination measure, right? To mean that rewrite steps from addition of 1 and 0 only takes 2 steps at most. Okay, at most only 2 steps. Okay, but on the other hand, if you look at the argument position, namely 1 and 0, this is kind of semantic value, namely semantic value also reflects the data size. Okay, and apparently this is not so strange, but if you see this kind of term, for instance, here we have some strange impression because termination measure was used for the next computation of addition. Okay, so if this stands for semantic value, this is okay. But once we apply interpretation of defined symbol, this actually stands for the number of rewrite steps, okay? The number of possible rewrite steps. So somewhat the roles are confused, okay? So here, if we separate these 2 roles, and then we have some benefit. Okay, so idea is this one. So we use 2 algebras. One is for semantic value, input values, okay? And another one is termination measure, okay? And here, complexity, okay? Time complexity is measured by this interpretation, okay? So for inside argument, first algebra is used, okay? And then the number of possible rewrite steps are measured by the second algebra, okay? And we also need to measure computation of complexity of argument positions. So we recursively call the same evaluation function for each argument, okay? And then actually we can relax the monotonicity condition to weak monotonicity condition. Orientation is only required for when measuring complexity. Okay, so this theorem says that this one is actually termination measure for our term. Of course, this is only the case that we use innermost rewriting. Okay, so let me illustrate this method by the same example. You see, for instance, if we compute the value of this term based on our evaluation function, you see, time complexity of this term consists of two parts, right? First one is calculation of this one, okay? The number of steps to compute inside argument. And then we also need to add the number of steps to compute addition of the corresponding value, namely 2 and 1, okay? And this is simulated by this evaluation function. Okay, you see here. Okay, this is 2, this is 1, this is 1, and this is 1. Okay, and how many steps do we need to compute addition of 2 and 1? Actually, just one step for applying second one, and in order to delete 0, we need another step, right? So this is actually 1 plus 1, so namely 2. Okay. What about this one? How many steps do we need to compute 1 and 1? Actually, same reasoning holds. Okay. So this is 1 plus 1. Okay, like this. So in order to compute inside argument, we need only 2 steps. And after that, we obtain 2, right? I'm sorry, I mean, the position of argument of plus was exchanged, but we need 2, right? So if we compute them, we obtain 2 plus 2, so this is 4. Okay, so this kind of rewrite sequence is interpreted to these values. Okay, so this is actually computation by A and B T, if this is T. Okay, so you see, we can. It's easier to obtain tighter upper bound for runtime complexity if we adapt to separate algebras. Okay, and complexity analysis is organized as follows. If we find a suitable pair of algebras, just checking orientation suffice. Okay, this is interpretation by A, and this is interpretation by A and B. Right, and you see, our interpretation for termination measure is based on linear polynomial. So runtime complexity is also linear time. Okay. Okay. I think I have explained enough for technical part. And now I want to illustrate the powerfulness of this method. Do you know the mechanism of insertion sort algorithm? Insertion sort algorithm uses insert function. This takes one natural number and insert it to sorted list. Okay, and this function behaves like this. Okay, so we first compare 4 and 1. 4 is larger, so this function goes down to argument position. And 4 versus 3, still 4 is larger, so insert shift to right position. Okay, and 4 versus 5. Now 5 is larger, so we put 4 here, and this is remaining part. Okay, and insertion sort is just to replace all const symbol by insert function. Okay, so this is insertion sort algorithm. If we use TRS representation, you see, just by performing some transformation techniques called unlabeling, we obtain such a rewrite rules. Okay, so this is okay. Previously, we had case analysis, but now case analysis is done by this auxiliary f function. Okay. Right, and insertion sort function itself is same, and we need some additional function. You know, TRS has no built-in function, so we need to specify greater than by ourselves. Okay, and we can automatically find such a suitable interpretation for insertion sort function, okay, based on by using SMT solvers. And you see, I sort function is quadratic polynomial, so innermost runtime complexity for insertion sort algorithm is quadratic time. Right. And also, let me little bit explain merge sort function. Merge sort was invented by perhaps John von Neumann, probably. And merge sort split a given list into two parts, and they must be almost equal number of elements. And after decomposing a given list into two, we perform merge operation. Okay, merge operation merges two sorted lists into single sorted list. Okay, and here the point is this is n log n time algorithm. And yeah, this is the mechanism. Probably you know list is okay split into two parts. And they are almost the same size. And O plus is merge function, okay? And we split, okay? And here we start merging phase, merge, and then we obtain sorted list, okay? And here, if you use term rewriting format, merge sort algorithm can be implemented by this code, okay? But let me replace this part by A and B, okay? So unfortunately, currently our tool cannot analyze this merge sort itself. So instead of comparing, instead of list over natural numbers, let me use list over A and B alphabet. Okay, and here A is greater than B. Okay, so just two element case. Okay, and our tool can find suitable interpretations, but this requires some very fancy functions. But all of them can be encoded into some linear arithmetic SMT problems. And here, this is important function, B function. B function is basically linear function, okay? But looks linear function, but this is step function version of linear function. This kind of function. You see, this is 2, 1, this is 2, 2, and this is 2 to the power of 3, like this. So basically, linear function, but stepped one. And actually, you see here, this horrible formula exists here, but this represents the complexity of merge sort function, okay? And here we have this constraint condition. So B of n can be replaced by n itself, okay, in big O notation. So this shows that the merge sort algorithm is n log n algorithm. Right, but perhaps now it is the time to show our tool. Our tool is called NL. And you see here merge sort. Okay, this is a description of merge sort algorithm. And if we put now SMT solver is running behind the tool. You see, this is the result of this tool. And yes means n log n time algorithm was proved. So runtime complexity is n log n. And you see, I mean, this is the interpretation that were found by SMT solver. Right. Okay, so now time is up. So let me conclude. Yeah, actually, we now automated runtime complexity analysis can handle merge sort algorithm. But you see here, we used two-value list. What happens if we replace this part by piano numbers? Actually, I'm not sure. Still, the runtime complexity is in this bound n log n. So this analysis of this system is our future work. Okay. So another instance, this is Euclidean algorithm. Actually, Euclidean algorithm, we can show n log n runtime complexity. Okay, now answer is yes. So n log n, but is this really optimal upper bound for runtime complexity? My guess is actually this system admit linear runtime complexity, I believe. But so far, I have no idea how to analyze this system. Okay, so let me conclude this talk. Yeah, we discussed about the notion of runtime complexities, and I explained some new technique for analyzing innermost runtime complexities. And now it captures insertion sort and merge sort. Future work is, of course, analysis of, general version of merge sort. But also, I want to analyze runtime complexity for balanced search trees like ABL tree or red-black trees. And also, graph-based algorithms are very popular for giving small complexity algorithms like Talian's algorithm. So I want to develop some new method suited for analyzing balanced search trees and also graph-based algorithms. Okay, yeah, this is the end of my talk. Thanks for your attention.
Okay, thank you very much now for this very didactical presentation and very interesting presentation. And once again for having accepted our invitation. Let's see whether I can synchronize the questions, but okay. I will see. I have some questions myself, but I want to give priority to the other attendants, and I don't know how this is synchronized with the. Okay, let's see whether. Okay, I see we have some comments here, but okay. Then I will start with my questions. The first thing is whether this method might be used to automate termination. Okay, the question is which kind of algebra will express the non-termination of an algorithm? Have you thought about that, or you start from a terminating algorithm and
yes.
This is a must for your method. Or it is possible to try to produce the algebraic expression automatically, and verifying it is not possible to produce this algebraic expression, then you answer that the algorithm is not terminating. This kind of automation.
I see. Yeah, yeah. That's really a good question. I mean, currently, this kind of method only can show upper bound of complexity or some termination of a given system. In order to detect non-termination, normally we need to use another method. And I don't know whether some uniform method exists for analyzing termination and also non-termination. And in the case of complexity analysis, actually, Jürgen Giesel and the group of Jürgen Giesel developed some loop detection. So they try to identify some format of rewrite rules, and then they have some classification of these rules. I mean, some relation. Some table of some syntax of rewrite rule and lower bound complexities. So in this way, they established some technique to show lower bound of runtime complexity. And actually, this seems very effective method. But as I said, I think currently there is no uniform method for analyzing termination and non-termination, or uniform method for analyzing upper bound and also lower bound of runtime complexities.
Mm-hmm. Okay, very interesting. Okay, I see some compliments and for the very clear presentation and things like that. But also, okay, the method requires the use of ASAT solver to deal with the solution of Diophantine equations, or to explore this space of solution of the Diophantine equations. What will happen when you have tried to move to more complex rewriting specifications like the Ackermann function, the 91 McCarthy function. We have polynomial expressing the complexity. How you will deal with this kind of situation?
Yeah, right. Yeah, thank you very much. Actually, in the current setting, I mean, we are only interested in polynomial functions. However, I think, I mean, exponential function, namely exponential time algorithm, would be also of our interest. So many algorithms based on some searching or enumeration exponential time algorithms. But there are very few techniques exist actually for non-polynomial expressions. And you see, I used some strange functions like max. This is, I mean, C function.
Okay. Yes.
Yeah, and these are, I mean, actually need some heuristics to find such an assignment. So I want to develop some specialized version of SMT solvers that are suited for complexity analysis. Yeah, thank you very much for your comment.
Okay. Well, I have another question. I have another question. No, it's a very interesting topic, and you know we are interested in automation of termination. Not exactly in complexity, but okay, we have think a little bit about that. One of the interesting aspects of rewriting systems is that they express the possibilities of parallelized algorithmical ideas in a very plain manner, no? Essentially rewriting disjunct radixes, you have a model of parallelism. And maybe this is a nice step thinking about not innermost reduction, but exploring with algebraic expression the possibilities of parallelization, for instance, in the merge sorting algorithm, in which you can rewrite simultaneously to the both branches of the expansion. Maybe would be possible to express the complexity of such kind of evaluation, parallel evaluation.
Yeah, thank you very much. Actually, I have never thought of such parallelism. But yeah, you are right. I think, I mean, for instance, parallel rewriting is, I mean, yeah, common notion in rewriting for normally analyzing for conference. But yeah, perhaps, I mean, this kind of steps can formalize the notion of parallelism nicely. And complexity analysis of parallel steps. Perhaps, I mean, no one tried, but I think, I mean, this is actually really good target to analyze. So, yeah, I mean, that would be really nice future. But yeah, thank you very much.
Okay, there is some question. You mentioned the possible fragment of graph algorithms, and Maria Eduarda asked whether there is some work in this direction.
Yeah, I see. I mean, yeah, I mean, of course, I mean, graph algorithm requires requires some stable representations, and normally terms are not suited for representing graph structures. But some of algorithms, like Talian's algorithm for computing strongly connected component, essentially based on graph algorithm, okay? And I think, this would be, good starting point for analyzing runtime complexity. And here, I think the point is runtime complexity itself is not enough to analyze graph-based algorithm. Probably we need to exploit amortized complexity for analyzing graph algorithms. And there are several work for analyzing amortized complexities, but so far I don't know how to connect runtime complexity to amortized complexity. So this research will be needed for having a progress in this direction.
Okay. Very nice. Then let me say I am very, very happy with your willingness to give this very nice and didactical presentation. And I think your presentation is also an invitation to our students to attend the courses, the lectures we offer in the graduate program in mathematics and computer science on rewriting. This is our introductory course on theory of computation. And this course is open to undergraduate students too, as a special course. Then I think they see rewriting is much more that matching and substitution and simplification. Rewriting is really a very, very, very powerful tool for analysis of computers, computational objects like software and hardware. And okay, I am really very happy. And also I want to highlight your references. You reference David Valley in this paper from Cynthia Kopp and David Valley on tuple interpretation. It's a paper from FCDS from 2021. And this is an honor for you because David Valley was a student from Daniel Enantes. He did his master in Brasilia and now is programming, one of the alumni from the graduate program in mathematics from the University of Brasilia, who is now in Netherlands working in his PhD. And I am very happy about this reference from you, the progress of David Valley, and I am sure you will see and we will cross David Valley in the near future. Now, thank you very much again for your very nice talk and for your willingness to give this talk. And okay, sorry, I am extending myself. It's late for you. Time to go to the bed in Japan. And then I say you are welcome to Brazil, to Brasilia in particular. And I hope in a near future we will be able to invite you to Brasilia in person. Okay? Thank you very much for the nice talk. Okay. I think we don't have the organizer, but we can stop now. And okay, see you soon in Brasilia or somewhere else. Bye-bye.